Hi everyone, and welcome back to educator.com. Today we're going to talk about fluids, starting a new unit specifically about density and buoyancy. Our objectives are going to be to calculate the density of an object, to determine whether an object will float given its average density, and to calculate the forces on a submerged or partially submerged object using Archimedes' principle. So as we start this new topic of fluids, let's talk about what a fluid is. Fluid is matter that flows under pressure. Things like liquids, a great example might be water, gases like air, and even plasmas like what you would get from an arc welder. Now, fluid mechanics is going to be the study of fluids and how they move. Fluids at rest, fluids in motion, forces applied to fluids, and then the forces exerted back by fluids. So to begin, let's get into density. Density, which gets the symbol Greek letter rho, is the ratio of an object's mass to the volume it occupies. Less dense fluids float on top of more dense fluids, and less dense solids will float on top of more dense fluids. Now, if density is the ratio of an object's mass to volume, density rho is mass over volume, and the units are going to be kilograms per meter cubed. Let's take a look at an example with the density of water. A single kilogram of water fills a cube of length 0.1 meter. What's the density of the water? Well, we've got our cube of water, and the length of each side is 0.1 meter. What's its density? Well, density is mass divided by volume. So that's going to be 1 kilogram, and the volume of a cube, length times width times height, is going to be 0.1 meter times 0.1 meter times 0.1 meter for a total of 1,000 kilograms per cubic meter. That's probably a good one to remember. Density of fresh water, 1,000 kilograms per meter cubed. Let's take a look at the volume of gold. It has a density of 19,320 kilograms per meter cubed. It's very dense. How much volume does a single kilogram of gold occupy? Well, if density is mass over volume, then volume will be mass over density, or 1 kilogram over 19,320 kilograms per meter cubed, or about 5.18 times 10 to the minus 5 cubic meters. Let's take a look at an example of things that are floating. Fresh water has a density of 1,000 kilograms per meter cubed. We just calculated that. Which of the following materials will float on water? Ice has a density of 917 kilograms per meter cubed. And if you've ever had a glass of ice water, you already know the answer. Ice will float on water. It is less dense than the water. Magnesium has a density of 1740 kilograms per meter cubed. It's more dense than water. It's going to sink. Cork, of course, 250 kilograms per meter cubed, is going to float. That's why we make bobbers out of cork when we go fishing. And glycerol, 1260 kilograms per meter cubed, is more dense, so it's going to sink. So those two will float because they are less dense. Let's talk a little bit about buoyancy now. Buoyancy is a force exerted by a fluid on an object that opposes the object's weight when it's in that fluid. The buoyant force, typically written F sub B, is determined using what's known as Archimedes' principle. The buoyant force is equal to the density of fluid times the volume of the fluid displaced times the acceleration due to gravity. And let's spell these out because they're easy to mix up. G, of course, is the acceleration due to gravity. The volume is going to be the volume of the fluid displaced by your object. And typically you just see this written as density, but I like to put the fluid after it to remind me. It's the density of the fluid that we need in this calculation, not the density of the object. So that's going to be the density of the displaced fluid. And of course, FB is the buoyant force. So let's do an example with the buoyant force. What is the buoyant force on a 0.3 cubic meter box which is fully submerged in fresh water that has a density of 1,000 kilograms per meter cubed? Well, the buoyant force, FB, is equal to the density of the fluid, rho, times the volume, V, of the fluid displaced, times G. So the density of the fluid displaced is 1,000 kilograms per meter cubed. We've got a volume of 0.3 cubic meters, and G we'll estimate as 10 meters per second squared for a force of about 3,000 newtons. Let's get exciting. Let's talk about a shark tank. A steel cable holds a 120 kilogram shark tank 3 meters below the surface of salt water. Salt water is slightly more dense than fresh water, 1025 kilograms per meter cubed. If the volume of water displaced by the shark tank is 0.1 cubic meter, what is the tension in the cable? Well, let's start with our free body diagram. There's our object. We have its weight pulling it down. We've got the buoyant force opposing that, and we also have a cable on it that has some tension in it, T. We want to find the tension in the cable. And if it's just sitting there 3 meters below the surface of the salt water, it's not accelerating, the net force must be 0. So we could write Newton's second law for the y direction, F net y equals tension plus the buoyant force minus the weight. And all of that must be equal to 0. And if we want tension, that must be equal to the weight minus the buoyant force. This implies then that the tension is equal to the weight minus, well, the buoyant force is the density of our fluid, rho fluid, times the volume of the fluid displaced times G. So that's going to be mass 120, G 10 meters per second squared, minus density of our fluid 1025 kilograms per meter cubed, times the volume of the water displaced by the tank, 0.1 times G, 10 meters per second squared. Therefore, our tension must equal about 175 newtons. Let's go to a favorite project in physics, building a concrete boat that floats. A rectangular boat made out of concrete with a mass of 3,000 kilograms floats on a freshwater lake. The density of freshwater, again, 1,000 kilograms per meter cubed. If the bottom area of the boat is 6 square meters, it's a pretty big boat, how much of the boat is submerged? Well, let's start with the free body diagram. We've got the weight of the boat down, mg, and we've got the buoyant force holding it up. Net force in the y direction then must be the buoyant force minus mg, and because it's not accelerating up or down, that must be equal to 0. Therefore, the buoyant force must be equal to mg. But we also know that the buoyant force is equal to the density of the fluid times the volume of the fluid displaced times g. Therefore, we could say then that density of the fluid times the volume times g equals mg. I can see right away there's a simplification we can make. We can divide g out of both sides. So we could also say then that the volume of our boat is going to be its area times its depth. So volume of the fluid displaced is going to be the area of the boat times how much of it's submerged, that depth submerged, d. Therefore, density of our fluid, rho fluid, times our volume, AD, must equal m. Rearrange this to find d, the depth of the boat submerged. D is going to be equal to the mass over density of the fluid times the area, or 3,000 kilograms, about 3 tons, divided by density of our fluid, 1,000, and the area, 6 square meters, or about 0.5 meters. About half a meter is going to be under the water. submerged. All right, let's take a look at a problem of apparent mass. A cubic meter of bricks have an apparent mass of about 2,400 kilograms when they're submerged in salt water with a density of 1025 kilograms per cubic meter. What is their mass on dry land? Well, what does that mean? Let's think about this for a second. If we were to go make a scale and on it we're going to put a bunch of bricks. There we go. And our scale's got a reading here. It has an apparent mass of 2,400 kilograms when it's submerged. The scale reads like it's 2,400 kilograms there. So what would its actual mass be on dry land? What would well, the mass isn't actually changing. What would the scale read on dry land? What would its weight be on dry land? Well, I'm going to start off with the free body diagram. We've got the weight down. While it's submerged, we've got the buoyant force up, and we've got the normal force from the scale. And as you know, scales tell you the normal force. So, if we wanted to write Newton's second law equation, normal force plus the buoyant force minus mg must equal 0 because acceleration is 0. The bricks are just sitting there on the scale. They're not accelerating. Therefore, we could write that, well, knowing that the apparent mass is 2,400 kilograms, that means the normal force, which must be mg, it must read that that's normal force of 24,000 newtons. So 24,000 plus the buoyant force, density of our fluid, times the volume of the fluid displaced, times g, minus mg equals 0. This implies then that 24,000 plus density of our fluid, 1025, times the volume of our fluid displaced, which was 1, times g, 10, minus 10m must equal 0. Therefore, 24,000 plus 1025 times 1 times 10, 10,250 equals 10m. Therefore, m must equal, I'll divide both of these by 10, 2,400 plus 1025, or about 3,425 kilograms is the actual mass. It appears to have a lower mass when it's in water because the buoyant force is helping lift it on the scale, providing some upward force to counteract that weight. Let's take a look at the volume of a submerged cube. We've got a cube of volume 0.002 cubic meters submerged in a glass of fresh water and attached to the bottom of the glass by a massless string. If the force of gravity on the cube is 10 newtons, what's the tension in the string? Let's see if we can't draw this out a little bit first. Feeble attempt at drawing a glass. There it is, and somewhere in the glass we've got our cube. And it is attached by a string to the bottom there. And we've got some sort of fresh water in our glass. All right, free body diagram again. Here we have our object. We've got its weight, mg, down. We've got the tension in the string down, and we've got the buoyant force up. And again, because it's just sitting there, it's not accelerating up or down, it must be in equilibrium. The net force must be 0. So net force in the y direction, which is the buoyant force, minus mg minus t must equal 0. Solving for the tension then, tension equals the buoyant force minus mg, which implies then that the tension must be the buoyant force, density of our fluid, times the volume of the fluid displaced, times g by Archimedes' principle, minus mg or that's going to be 1,000, since it's fresh water, kilograms per meter cubed. Volume displaced, 0.002. G is 10, minus mg. Well, it gives us the force of gravity on it is 10 newtons, which is its weight, which is mg, minus 10. Therefore, the tension comes out to be 1,000 times 0.002 times 10. 20 minus 10 will be 10 newtons. Let's try one more practice problem here. Determining density. This one's a little bit more involved. The density of an unknown specimen may be determined by hanging the specimen from a scale in air and in water and then comparing the two measurements. If the scale reading in air we're going to call Fa and the scale reading in water is Fw, let's develop a formula for the density of the specimen in terms of the scale reading in air, in water, and the density of the fluid. I'm going to start with the free body diagram. When we're in air, we've got mg down, and we've got Fa on the scale up, and those will be balanced because it's sitting on the scale at equilibrium. When it's in water, our free body diagram is going to look similar, but a little bit different. We've still got the weight down, but now we have the buoyant force up along with the force of the scale, Fw. So, starting with the water, we've got Fb, the buoyant force, plus the force of the scale when it's in water must be equal to its weight because it's at equilibrium. And we also know that the force of air is equal to mg. So I could rewrite this as Fb plus Fw equals Fa. But that buoyant force is equal to rho fluid Vg. So I could rewrite this then as Fa minus Fw, with a little bit of rearranging, must equal density of our fluid times the volume displaced times g. Now we've got to take another step that's maybe not quite so obvious. Let's take a look, and let's say that the density of our object is equal to the mass of the object divided by the volume of the object. Therefore, the volume of our object is equal to the mass of the object over the density of the object. I'm going to use that as I rewrite this equation to say that Fa minus Fw equals, we've got our density of our fluid, but I'm going to replace the volume displaced with my new formula for volume, mass of the object over density of the object. So mass of the object over density of the object times divided by the scale reading in air minus the scale reading in water. Hopefully that gets you a good start on density and buoyancy as we start this new section on fluids. Appreciate your time and make it a great day, everyone.